So hello everyone. Let's talk about object lifetime. So object lifetime is a core concept of the language, and really understanding how it works, it's essential for building really correct and efficient code. So being this a very basic concept, not really concept in the C++ concept, but this being such an essential part of the language, I want to get something straight regarding some expectations from this talk. So what you can expect from this talk is to get an overview of how the lifetime of objects work in C++. I'll also be covering a little bit about RAII and what it is and what's the relation with object lifetime. But really the most important part that I consider here is going a little beyond this basic part of lifetime, and of course talking about the common pitfalls that we might fall when we are talking about objects. What you should not expect from this talk is an overview or justifications of the behavior of the language based on non-value category. I know it's essential, it's a very important part, but my goal for this talk is to get it more beginner-friendly as I could. So although we know, most of us here know a lot of R values, L values, and a lot of these things, I'll try to not go on that direction to showcase and to explain some of the things here today. Also, for the sake of this talk and for the sake of object lifetime here, I'll be ignoring the existence of unions and arrays. They have this whole set of specific rules that can get a little bit more deep than I want to showcase here today, or than the time that I have to talk here today. And also, unfortunately for many, I will not be having any kind of assembly here. This is meant as a joke, of course, but what I really want to stress out here is that this talk is really meant for beginners. I want that if someone is starting with C++ and get to watch this talk, they will have a more deeper understanding of the language. But at the same time, I do expect that many as us here that might already work with C++ for a lot of time might also get something from this talk as well. So when I sit down to put this talk, I have this great idea of going to the standard and trying to learn from the standard what is object lifetime anyway. So I went out, I found the standard, I started to read, and then I was bombarded by all these concepts that is not really a part of our day-to-day routine as developers. And this is just an example. This goes on for, I think, maybe 5 pages as of the standard for C++ 17. But then when I was Googling around, I ended up finding the FAQ for the standard itself that states that the standard is not meant to teach C++. So yeah, I did wish I knew that sooner. So if you want to leave now, leave with this message that don't go to the standard for learning C++. There are much better reference. And although I'm saying here throughout this presentation, I will go back to the standard and try to help understand from the standard what is object lifetime and all the details in between. So hello, my name is Thamara, and I'm a software engineer working at Cadence. I like to say that I've been learning C++ for 10 years now. It was kind of an unfortunate mistake when I applied for a position, an internship position of C++ developers, knowing just C. But I thought, if I know C, might as well know C++, right? I was very wrong. But that's okay. I'm very happy with the outcome for this. And when I say that I've really been learning, it's not an exaggeration. So this whole presentation was motivated by problems that I hit just a few months ago when, even though I thought I knew how the lifetime of objects in C++ would work, I was proven wrong. And of course, I pay with my time for debugging and questioning the compiler and all the in-between that we usually do when we can't really explain the behavior that we are seeing. And I can't decide if the namespace for the standard library is pronounced stud or std. I might as well try to avoid talking about that in this talk. But if you see and don't notice any kind of consistency, then you know why it is. So let's go back to the standard. When we see the part that specifies when the lifetime of an object starts and ends, there is actually two concepts here that are relevant for us. The first one is regarding storage, and the second one is regarding non-vacuous initialization. So in one slide, what is storage duration for those who might not be remembering what it is? So as of C++11, although in C++17 we removed one, but for the sake of this presentation, let's consider that we have 4 types of storage duration that an object can have. So the first one is static, which is described and specified by the keyword static. And basically what it means is that this object is allocated when the program starts and is deallocated when the program finishes. So basically we only have one instance of that object. The second type is a thread storage duration, which is specified by the thread local. And it's similar to the static one, but for threads. So we only have one object of that given, of the specified type per the thread duration. So the object will be allocated when the thread starts and deallocated when the thread finishes. We also have the dynamic type, which is something that is more familiar to us, which the lifetime, or the storage duration, is defined by the new and delete keywords. And finally, we have the automatic type, which is pretty much anything that is not static, thread, or dynamic. So everything else is considered to be automatic, and its allocation and delocation might change depending on the context that they are declared. The second thing that I have mentioned there, I do have a question. Sorry, I could not hear that.
You don't mention here static variable of the function.
Oh, it's a variable. So I'm talking here towards variables here.
No. It's talking about inside a function you can declare.
Oh, yes. I'm talking not about, I mean, there is a lot to say about storage durations and everything. And it's not really the goal here, actually. So throughout this presentation, I'll be mainly focused towards more, let's say, simple declarations of objects using dynamic or automatic duration. So yeah, there is a whole bunch that we can say more, but it's not really the intent of this talk. And feel free to keep asking questions. I'll try to hear and repeat that as I could. So the second thing that we can talk about is about non-vacuous initialization. So when I first read this, I was trying to get around, but the standard itself tried to help us and to explain that a non-vacuous initialization is basically an object that is initialized by a constructor other than the trivial default constructor. So to simplify things a lot here, what I mean by non-vacuous initialization is pretty much a class object that has a constructor, even if the constructor is empty. If you declare that constructor, it is considered non-vacuous initialization. And of course, there are many other rules, such as if a class doesn't have an explicit constructor, but has virtual functions and so on. Again, not really the focus on the details of what specifies exactly the vacuous initialization or not, but just to give an idea, what would be considered a vacuous initialization would be that plain old types or plain old data, PODs, right? That are the basic types. So their declaration does not really initialize those. And the same goes for structures or class that doesn't have anything, that are empty, or even those that have only the basic types. And again, for the sake of this talk, we will focus more towards the objects that has non-vacuous initialization, just because they, educationally, they are better to handle and to showcase the lifetime. So let's talk about constructors and destructors. And wherever we talk about that, we usually have some example like this, where we can create some object and create constructors, copy assignments, and so on, and add some logging messages just to see what's happening at which point of the program. And there is actually a reason for that. It's very easy and, again, educational to do like that. So that's what I'm doing as well. So during this presentation, whenever you see code, you have a link to Godbolt. Thank Matt Godbolt for Compiler Explorer. And although this is a very simple example, as we go on, there will be more interesting case. So let's take a very quick look through these examples here. So if I have a structure here being declared, I will see the constructor being called. Then I have a new scope in which I have the declaration of another object full. Then I see another constructor here. And because the scope for this variable has finished, then of course we will see the destructor being called for that B object. And when the main function finishes the scope for the variable A, the object A ends, then the destructor finishes. And this is obvious. We can obviously do the same for dynamic type of variable. So in here we declare a pointer. So the pointer itself is not the object, right? And in here, it doesn't really need the scope here. But in here, I do create a new object by calling new foo. And the address for this object is assigned to the pointer that I have declared A. So in this point at line 9, the object is still alive. Of course, we are not deleting that until we hit the line 10, where we explicitly delete that object, in which case we will see the destructor being called. So just from this, we can go back and really understand at least a high-level version of what the standard specifies as the lifetime of an object. And before we talk about that, I am using here the last draft that I found for C++17. And the main reason for that is that I am using C++17. So many of the things that I have learned and I'm showing here today, they were things that I have faced. So it was close to me. So I did choose C++17. I will mention in some points what is the difference that I found for more modern standards. But because we are actually kind of abstracting some things out, it's pretty much the same when we are talking about the definition of lifetime. So as the standard says, lifetime of an object starts when the storage is obtained and when the object, if it has a non-vacuous initialization, if that initialization is complete. And the complete part is something that might not be very obvious here, what is complete in this case. So going back to the example of a class here, we are creating this object obj. So we will go to the constructor of this object. We might do something, for example, allocating some memory for that. And then something happens and we throw an exception. So this exception was thrown from the constructor of this object. So this means that it's not fully initialized. So the execution for the constructor here, it will halt. It will go back to the outer scope here. And as we finish this scope, for example, in this main function, the memory that we have previously allocated on the start of the constructor will remain there. The delete function or the destructor of this object will never be called because, again, the lifetime for this object never really started. If we use some sanitizers, we might see, for example, in this case, that we had a memory leak. So if this is the beginning of the object lifetime, the end is pretty much the inverse of that, right? So the standard says that the lifetime of an object ends if it having a non-trivial destructor, that destructor call starts, or the storage is released. So the storage released, it could be seen something like if you have a vector and you pop something from this vector, the memory from the vector will not be released right away, but the object will still be destroyed. And with this really basic overview of lifetime, we can already talk about some of the most powerful techniques that we have on C++, which is RAII, or Resource Acquisition is Initialization. And this is relevant here because as per the definition of RAII, we have that this is basically connect or tie the resource acquisition and deletion to the object lifetime. So whenever we are talking about RAII, usually we have some examples like this where we have a dynamic array, we initialize or we allocate that array on the constructor, and then we can declare that, for example, on line 8 here, we can use this array as we want, and as the object goes out of scope, as the dynamic array R, it's the lifetime for this object ends, then the destructor is called, and then the memory that was allocated within the structure, the object here, is then released. But of course, this is just one example. There are many other more maybe useful or more frequent usages of RAII in our life. So heap memory allocation, kind of as in the example that we have, mutex handling threads, file management, and all of those are just a few examples, and they are a few that are actually available in the STL. So in the standard template library, we will find some cases such as the unique pointer, shared pointers, which are far more better options for handling memory than, of course, trying to call that new and delete by hand. You might have lots of problems. We have other options to deal with text threads and files as well. Although all of those, and I have first have tried to signal here with the asterisk there, is that there are some things that we can argue regarding exactly what is our RAII in the concept that maybe, for example, OF string is not really RAII, but for the sake of this talk, let's not dive into that. But when I was talking and sharing this presentation with a friend, he actually mentioned something to me that I never really put much thought into that, which is actually not only RAII is in the STL, and those examples that I have given, RAII is most of the STL. So maybe most is still a strong word here, but let's take the string, for example. Internally, we will have a buffer. That buffer will be constructed and managed during the lifetime of that string object. So this is an implementation or end use of RAII as well. Do we have any questions so far? So if I were to stop here, I think this is already kind of a brief explanation of object lifetime from start to finish. But that's when I realized that maybe I was too nice, or maybe I could improve the name of this presentation. Because yes, we can talk about when it starts, when it ends, but really the core thing that I want to share here, that I want to have you notice here, is actually the trick part all around that. So let's talk about the trick parts all around the object lifetime. And for that, I want to invite you to play a little game with me. I don't know if you know Mad Libs. I personally didn't really try. I think this is more maybe an American tradition, but I do notice that I do know kind of from movies and everything like that. This is kind of an old game where you have this story, and you ask people around you for some types of words. So you might ask for a verb, for a noun, for a color, whatever, and you fill in the blanks here. And at the end, you have a story that is very unique towards this, towards who you are playing with, and usually ends up being really funny. But of course, this is a C++ conference. So instead of having like this text here, we are gonna play with a different context. We are gonna have this code, and we are gonna fill in the blanks here regarding what is returned from a member function of an object, and we will initialize variable val in different ways. And these ways will be mostly with an object full, const, non-const versions, reference, or just value itself. And actually, this idea came to me when I was reading Abseil. I don't know how to pronounce that, sorry for that. But I want to thank Titus Winters for actually lending me some of these, because this was all, it fit perfect for this presentation to really introduce some of the things that I want to talk here today. If you don't know this site, it has a huge collection of C++ tips, so check it out. So let's start, and we are gonna go through 9 cases here. I do leave as a homework for the other that will be missing here. But let's start by returning a full by value and initializing that variable full as full. So what do we have here? So anyone has a guess in terms of what might happen regarding how many objects will be created or might exist in this code at some point? 3? Yeah. So let's go a little bit beyond and add some implementation here of this get full returning a object. So in this case, we have a temporary object, right? So the temporary plus the var, it should be true. So this might be something that for someone who is starting with C++, or maybe someone who might not be used to having move semantics in place, might have different answers for us here. Because it can be very intuitive to think that we are talking about 2 objects. We will create that full, it will get returned, we will call a copy constructor or a move constructor, and we actually have the construction of 2 objects. But look for us, the compiler has a very nice optimization that help us in this case. So in this scenario, what we can potentially have is the temporary being initialized directly on the storage location for that variable that we define on the main function. This has a very cool name, which is return value optimization, or RVO. And usually when I was starting with C++ during the reviews, and I was trying to avoid having to construct more or calling copy constructions or move constructions on some objects, and people on the review were just like, RVO, RVO, RVO. So this is what RVO means. And if we tweak that function a little bit, for example, for creating the object, then do some kind of manipulation, it might require to initialize this object in some more heavy way and just return. In this case, we still might think that we can have some kind of move or copy here. But again, the compiler is allowed in most cases. We'll be able to do this optimization again of creating this object directly on the place that was reserved for the variable val. This is also another type of return value optimization. We give that a different name. We call that named return value optimization. But again, it's a kind of an optimization. And although it's not really the focus of these talks, I want to share with you some cool way that you can try to play around and understand when the name return value optimization happens, which is, for example, doing the following. So again, very simple example. We have a function that, in this case, we are passing not only have the value being returned, we can do some kind of initialization in there. but we will pass on the address for this variable that we are creating on main. And by having that inside the function, we can actually compare those pointers and see that this will actually work. So we are dealing with the same piece of memory for both cases, for both the function, for both the object that we are creating inside the getFull function, as well for the full that we are creating on the main. And we can even play around with making a little bit more complex by adding some brains. The compiler is still able to do the optimization. And so I continue playing with it and trying to mix and match and see that in action and getting really cool results for that. Until I noticed that this code worked. I could see, although I'm missing the assertion here, we can see with some debugging messages that we do have return value optimization here. But this was running on Clang. This was the latest version of Clang that I was using on Compiler Explorer. When I try to use with GCC, then I see that it's actually being called move construction. So again, not really the focus, but just to put a pin on that, this kind of optimization, often also referred as copy elision, it's something that the compiler is allowed to do. It's not mandatory, and there is a whole bunch of rules for that. Just so we really end these things here, generic rule, just to give some ideas or just to give some path towards understanding that, you could see that the RVO is really, it's potentially being applied when you have a function that is being, that has some value being returned by value, and you are creating a variable of the same type, and it's that variable that you are returning. So when this happens, usually, again, not guaranteed, you will have some kind of return value optimization. But for the sake of this talk, let's consider that in this case, at most, we will have some kind of move here. Let's go into another example here. In this case, we are returning a reference to full, and we are initializing the variable with full. So we are basically just copying the variable, right? And yeah, we are just copying that. We might call the copy constructor in here, and it might be something that you are indeed expecting and willing to do, as this way you have control over the lifetime of this object that you are declaring on line 8 here. The same is obvious true if you had the function return a const reference as well. But let's talk about some more interesting case. In this example, let's see what would happen if we were to, yes. So let's return a const reference to full, and let's initialize a const reference to full. I promise interesting case, but I give you this. What's the problem, right? I mean, this is fine. This will work. There is nothing really interesting here, or is there? Because we are talking about lifetime of objects. And by doing this, if you have, for example, an implementation that returns the member full that we might have under obj, then what you are actually doing, maybe really not putting too much thought into that, is that you are binding the reference, or you are binding that reference that you are creating on main to the lifetime of something that you might not have control over that. And this is a very common case of the creation of dangling references. So what's dangling reference? So let's just illustrate that with, again, just let's keep full here with some member, some integer member, and we have the object obj returning a reference to this object for this member that it has internally. So we can create an object. In just using a new here just for me to be able to control the memory better. But we will see the creation for foo. We can get the reference for that. We can get the reference for that object which is stored inside obj. We can, for example, print out and we'll see the result that we are expecting. And then we delete this object. And when we go to access that variable, that reference that we have again, then we get undefined behavior. So put like this is very easy to spot on the problem, right? But when you are dealing with a more complex and bigger code base, this might be very hard to spot on, and you might need to end up having to spend a lot of time debugging, or use of sanitizers, and a lot of other things in order to guarantee the safety of this kind of code. So yeah, it's fine to have something like that, but we should be cautious about that. And of course, the same would go if we were to return a non-const reference for foo, as well if we were to initialize a val as a reference, a non-const reference. In this case, not only we have this binding of the lifetime of this reference to an object that we can really control, but we also have the side effect that modifications to this val will reflect on the original object, which in many cases, maybe in the majority of the cases that we have, is exactly what you want. Either the const or non-const version is exactly what you want and will work. But this being an object lifetime, I could not go without saying that you should be careful of dealing with objects that you can't really control the lifetime. So let's go into another example here. This is already our 7th case. In this scenario, we have get foo returning a const reference to foo, and we are initializing a non-const reference to foo. Any guesses on what might happen here? Yes, it won't compile. We are casting away the const, not really casting away, but we are dropping the const here. So thanks, compiler, for not allowing us to do anything incorrect here. And what happens if we change get foo to return a foo by value? And we are still declaring val as a non-const reference. Any guesses? We are getting there. It's not lifetime extension. Yes. Yes. Exactly. So we are getting a compilation error in this case. And again, the compiler is not allowing us to do wrong things. So if I do change to initialize, instead of a non-const foo reference, a const foo reference, it should not allow me to do that as well, right? Well, it does. And as already mentioned, in this case, even though we still have a reference, a const reference in this case, and a temporary, this is well-behaved code in the sense that this is allowed and this is very well defined. This is lifetime extension. So before we jump into explaining lifetime extension, which by the way is something that I believe for the first time that I saw, I mentioned I was doing a review and I saw that and I was like, how is that working? And I was trying to talk with the person who was doing that code, and the person was not really understanding my question because I was really surprised with everything that was happening. And so far it's one of the maybe strangest behaviors that the language that I can think of that are easy to kind of see, especially when we don't have, if we don't have the const, then it's a compilation error. So before we really dive into the details of lifetime extension, let's talk about the lifetime of temporaries. So I have mentioned that I've been using the standard. I'm using C++17 standard. And in the context of this talk, this was the place that I noticed more difference between, for example, C++17 and C++20. But the difference that I saw were more towards being more explicit of what exactly can generate a temporary, what are the scenarios of the exceptions that exist. And a lot of that is actually described in terms of values and the types of things that I have said that I was not gonna mention here. So for the sake of this talk, I think this already illustrates a lot of what is the lifetime of temporaries and the problems that we will see that come from that. But I do invite you all to check it out. Maybe not go into the standard right away, but maybe check some other sources like CPP reference, for example. But what the standard, again, the 17, C++17 standard say, is that we are gonna skip what the temporaries are, and we're gonna focus on when the lifetime of this temporary is finished. And what the standard says that the temporaries objects, they are destroyed as per the last step of the on evaluating the full expression that contains the point where they are created. Little bit complicated, what is the full expression? So let's see an example that I think will be better explained. Again, we are just gonna have some very boilerplate code of an structure bar and a structure full. Again, not again, but sorry, I'm really bad with names. So it's full and bar. And full actually has a member function that returns a bar, just for the sake of the example. And then we have two functions. We have the function do something that receives different versions or different parameters. And we have this do something else that is here really just to help us illustrate what is the full expression. So you may already know that the order of evaluation for parameters in a function is something that is not defined. But of course, the implementation will define something. As a matter of fact, if I'm not mistaken, and I cannot say for every version of compilers, but on Clang, it's left to right. And on GCC, it's right to left. I don't know other compilers. And again, I don't know other versions, just as a fact here. And just for the sake, we are gonna treat that left to right. So what we have here is that we are evaluating first the parameters for the function do something. So we start with the creation for the full one. And again, because the standard says that the lifetime of these variables, that these temporary objects that are created within the context of a full expression only gets its lifetime and only destroyed as the last step, then we will not see any destruction here. This full one will keep living here. And the same for foo2, even though we are accessing some member of foo2 will still be alive. And foo3, we are creating a new foo, we are getting a new bar from that as well. We are seeing foo and bar being created. And I added this example here because whenever we are talking about dangling reference, I think this is a very common case of that we usually hit, which is when we try to access, for example, the C string for a string. So usually when we do that, it might end up bad. But in this case, I just want to showcase that we are going to create the string. We are not going to delete the string here. And in the end here, we have the closing, I forgot the name for this, the parentheses, thank you. We have the closing parentheses for do something, and then we have a comma that will later evaluate do something. So we have created these objects, we will then evaluate this do something, this object will keep alive, Then we will go to the execution of this do something else. And only when we hit the semicolon, then we have the lifetime of these objects getting to an end. Because this is only when we have the full expression really finishing. So in this case, we will just see all these objects being destroyed. Maybe more interesting case of these objects, these temporary objects preserving its lifetime during the execution of the full expression is if we have something like this. So in this case, we will create a foo. This is a temporary object that we pass on for a function that takes on a reference for foo and just return that reference. Then we have do something that, again, we will do something, it doesn't matter. And just at the end of all these expressions, of all these executions, then foo will be destroyed. If we were to, for example, extract the execution of this return temp ref to some variable, assign that to a constant reference, and then use that constant reference to do something, to call do something, then we will have undefined behavior. So this is the rule, but then we follow with the exceptions. And the exceptions is actually what justified the example that we saw of lifetime extension. So what is this exception? So the standard says that there are 3 contexts in which the lifetime of the temporary might persist for a different time or might be destroyed in a different time than the end of the lifetime of, or than the end of the full expression. The first and second context we can ignore, but the third one is regarding when function or when temporary objects are assigned to a reference, are bounded to a reference. That in this case, the lifetime of that temporary persists for the lifetime of the reference itself. So again, let's take a look at an example. We have foo with an integer, and we have some different functions, one that returns by value, that member, that integer, and another that returns a reference to that integer. And then we can try to play around with that. So the first case on line 12 here, we have the creation of a temporary foo, and we assign that to a reference, a constant reference. So as per the rules that we have saw, this will extend the life of foo. So we will see the creation of foo here, and its deletion or the destructor of foo will only be called when the function finishes, when the scope for this reference finishes. There are some details of exactly what defines when the lifetime extension comes into play or not. I have an example of a more straightforward one, but again, this is a bit more complex here. But the lifetime extension also comes into action when you are accessing a member of that class directly. So in this case, we are creating a new foo, and we are accessing that integer, and we are creating a reference to that integer. This will still trigger the lifetime extension. If we were to create another one, another foo, another temporary here, and access or call the function I, in this case, I just return by value an integer. So in this case, we have lifetime extension, but not from foo. So in this case, we actually see foo being created and destroyed on the same statement, right on that semicolon there. But I itself has the lifetime extended. If we were to create an example, in this example, another temporary, and call the function that returns a reference, then in this case, lifetime extension doesn't come into action, and we will have the creation and the deletion within this expression, and this will actually cause a dangling reference. So based on this rule that if we have a temporary being created and bounded to a reference, then the lifetime for that is extended. Then this is a problem because if we go back to this example, we have actually been a temporary being bounded to a reference. The reference is the parameter of return temp ref here, and so it should finish. So, questions? Yeah.
Go to the previous slide.
Yeah.
Where? Yeah, this one. Line 13.
Yeah.
Why we don't see destructor of full?
So yes, these are the rules that, as I mentioned. So the question is why we are not seeing the destructure of foo in the line 13? So there are different rules and more complex rules than I wanted to approach on this talk. But there are some scenarios where even though you are accessing a member or even though you are doing something that is not capturing the temporary object directly, the lifetime of this object is extended. One of these rules is when you are accessing directly a member for this temporary. So this is why we don't have the destructor of foo being called. As a matter of fact, ignoring the foo 3 and foo 4, foo 2 and foo 1 will only be destroyed when this reference go out of scope in the end of the main function. So as I was mentioning, if we take on this rule, then we are breaking what we already defined. So the standard actually goes to add exceptions to the exceptions. So it goes to say that, again, if we are bounding a temporary to a function parameter, then it will preserve until the end of the full expression. And we also have two others that I'm gonna leave here. You can check it out. I will leave, of course, the slides available later. You can check it out and maybe even compare to new standards. But yeah, it's kind of complicated when we start to think about rules and exceptions, and the exception has an exception. So this is where it can get pretty painful. But you might think, okay, I know this now. I know a little bit better about lifetime extension. I know that my temporaries that I'm passing on to function parameters that I'm evaluating in a full expression, I know better how they live. I'm safe, right? But then things appear to when you are not expecting. So the last case that I want to share with you here is regarding range-based for loops. And maybe if you are more connected to the standards and the discussions, you might see what I'm going. But if not, let me take you there. So in this case, we have a vector being returned by value, and we are going to iterate on that in different ways. So the first way, we are just creating an object and iterating on this object, and 1, 2, 3, right? Exactly what we want, exactly what we expect. Nothing special here. If we were to construct that object directly on that for loop, on that statement, that expression, we still have 1, 2, 3 as expected. What happens now if instead of having that function that returns a vector, I have an object? This object internally has this vector and provides us with a method to retrieve that vector through returning a const reference to that vector. If I were to create this object and then call, and then iterate through that, I will see 1, 2, 3 as expected. Nothing strange here. If I were, for example, to access directly that member, again, 1, 2, 3. And if I were to construct that object and access through a get function that returns the const reference, then this is undefined behavior. And this is a very trick one to understand, because I was just saying, and when I first saw this, I was thinking, but how could it be? Isn't that the full expression? Turns out it isn't. And to share with you what's really happening here, I'm gonna use one of my favorite available tools out there, which is CppNorth, that kind of show you close to what the compiler is seeing, specifically when you are dealing with features that are more towards synthetic sugar, which is in the case of the range-based for loop. So if we have this example where we are creating a temporary and accessing that directly, then we will see that the for loop, this range-based for loop, will become something like that. It's a bit complicated, but let's go in parts. So on line 2, we are creating the object, accessing that, and we are assigning that to a variable range. And then on line 3 and 4, we have the definition, the declaration for begin and end, and then we use more like the traditional for loop in order to iterate on that. Notice that here we are actually having some kind of reference lifetime extension. If we were to look, and of course this will cause any access to be valid, it will work as we are expecting. If we were to take a look at the other example, the one where we are creating the object and then accessing that through a getter function that returns a const reference, then it becomes something like that. And in this case, we don't have lifetime extension because of what I have shared with you before. So we are creating values, the object that contains that vector. We are returning, we are getting a reference, but the object dies right at the end of this statement, right at the same column. So the next lines here, it's basically working with a dangling reference, which is not good, right? So this was actually fixed and addressed for C++23. And the fix that we have is actually another exception. So I share with you that there are 3 exceptions to this lifetime of temporaries. There is now 4 contexts, and which one of those is actually regarding range-based for loops. So I'll leave you to it to take a read at that. It's a very interesting reading to get to know more of how these things are being discussed. Any questions? So we actually reached the end of this talk. So I do hope that I was able to pass along some more information about lifetime of the objects, when it starts, when it ends. Again, remind everyone how much our AII is great, how much it's everywhere. Talk a little bit about return value optimizations. It's not really the core, but I could not let go of sharing with you a few details of that. Talk about dangling reference when they can appear, especially if you are dealing with objects that you don't really have control over their lifetime. Talked about lifetime of temporaries, its exceptions to the exceptions, and everything in between that you might fall into when you are coding. And hopefully I have here, what I have shown here, will save your future self sometimes. So thank you a lot.